Hi, I'm Taki Hasan Rafi, a PhD student from Hanyang University, and today I will present our work titled Learning from Unknown for OpenSet Test Time Adaptation. This work is a collaboration between Hanyang University and Oracle AI. The main idea of this paper is simple but important. In OpenSet Test Time Adaptation, most existing methods try to detect unknown samples and discard them. However, we show that some unknown samples actually contain useful semantic information, and if we learn from them carefully, we can improve adaptation performance. Let me first introduce test time adaptation, or TTA. In many real-world applications, models are trained on one distribution, called the source domain, but are deployed in a different distribution, called the target domain. For example, a model trained on clean images may be tested on images with noise, blur, fog, or lighting changes. This mismatch between training and testing data is called distribution shift, and it can significantly degrade model performance. Test time adaptation addresses this problem by allowing the model to adapt itself using unlabeled target data during inference. The key advantage is that no source data or target labels are required during deployment. However, most existing TTA methods assume a closed set scenario. This means the source and target domains share the same label space. In reality, this assumption is often violated. The target domain may contain unknown classes that were never seen during training. This leads to the OpenSet Test Time Adaptation, or OSTTA setting. In OSTTA, the model must adapt to known classes and detect or handle unknown samples that do not belong to the source label space. This makes the problem significantly more challenging. Existing TTA methods struggle when unknown samples appear. Most current OpenSet TTA methods follow a simple strategy: detect unknown samples and discard them during adaptation. While this avoids negative transfer, it introduces another problem: information loss. Not all unknown samples are harmful. Some unknown samples may share useful semantic features with known classes. For example, an unknown animal class may still share texture or shape features with known animals. If we discard these samples completely, we lose valuable information that could help the model adapt. Therefore, our key insight is, not all unknown samples are harmful. Some unknowns are semantically useful, and we should leverage them during adaptation. Based on this insight, we propose LU-OSTTA, which stands for Learning from Unknown for OSTTA. Our framework is designed to identify useful unknown samples, downweight harmful ones, and use the useful ones to improve adaptation. The framework consists of three main components: dynamic energy threshold, optimal transport pseudo-label refinement, adaptive prototype weighting. These components work together to selectively learn from unknown samples. The first component is the dynamic energy threshold. In many OOD detection methods, a single global threshold is used to separate known and unknown samples. However, this is problematic because different classes may have different energy distributions. A global threshold may reject useful samples or accept harmful noise. To address this, we compute class-conditioned energy statistics. This produces a dynamic threshold that adapts per class. Instead of fully discarding unknown samples, we apply soft weighting. Low-energy samples receive higher weights. High-energy samples are down-weighted. This allows the model to retain semantically useful unknown samples. The second component is optimal transport-based pseudo-label refinement. During test time adaptation, pseudo-labels are often noisy. Teacher models may produce overconfident predictions, especially for unknown samples. Instead of refining labels for each sample independently, we use optimal transport to align teacher predictions and student predictions at the distribution level. This alignment is solved using the Sinkhorn algorithm. The result is a smoothed and calibrated pseudo-label distribution, which reduces noise and improves stability during adaptation. The third component is adaptive prototype weighting. Even after filtering and refining labels, some unknown samples may still be harmful. To address this, we maintain frozen source prototypes and updating target prototypes. For each target sample, we compute its semantic similarity to the source prototypes. This produces a semantic weight. Samples similar to source classes receive higher weights. Distant samples are down-weighted. We then use a contrastive loss to align useful features and entropy regularization to prevent collapse. This ensures that only semantically useful, unknown samples contribute to adaptation. Now I'll present the main experimental results. We evaluate our method on CIFAR-C and CIFAR-C under the OpenSet setting, where the target domain contains both known and unknown samples. The table compares our method with several baselines, including source-only model, standard TTA methods such as TENT and EATA, and recent OpenSet TTA methods like Unient and SOSTTA. On CIFAR-C, the previous best accuracy is 86.23%, achieved by SOSTTA. Our method improves this to 89.34%, giving a gain of more than 3 percentage points. We also observe consistent improvements in open-set metrics. For example, AUROC increases, FPR at 95%, TPR decreases, and OSCR improves by several points. This indicates that our method not only improves classification accuracy on known classes, but also provides better separation between known and unknown samples. On CIFAR-100C, which is a more challenging dataset with 100 classes, we again see consistent gains over the best prior method. This shows that learning from useful unknown samples is effective even in more complex classification settings. We also evaluate our method on the Tiny-ImageNet benchmark, which is significantly more challenging. Tiny-ImageNet contains more classes and more complex visual structures, making both adaptation and open-set detection harder. Even in this setting, our method consistently outperforms all baselines across all metrics. In particular, we observe improvements of over 3 percentage points in accuracy and similar gains in AUROC and OSCR. This demonstrates that the proposed components are not specific to CIFAR-style datasets, but generalize well to larger and more complex scenarios. Next, we present several analyses to better understand the behavior of our method. First, the ablation study. We start with a baseline model without any of our proposed modules. In this case, the accuracy is only around 64% because the model struggles with unknown samples and noisy pseudo-labels. When we add only the dynamic energy threshold, performance improves significantly, since the model can better separate known and unknown samples. Similarly, when we add only the optimal transport pseudo-label refinement, we also observe strong improvements, showing that label noise is a major issue during test time adaptation. When both components are combined, the performance becomes comparable to strong open-set baselines. Finally, when we add the adaptive prototype weighting, the model achieves the best performance, reaching nearly 89% accuracy. This confirms that all three components are complementary and necessary for optimal performance. Second, we compare different confidence thresholding methods. We evaluate standard approaches such as MSP, max logit, and energy-based thresholds. Our dynamic energy threshold significantly outperforms these methods across all open-set metrics. This shows that class condition thresholding is more effective than using a single global threshold. Third, we analyze robustness to learning rate, batch size, and other hyperparameters. The plots show that our method maintains stable performance across a wide range of settings. Even with smaller batch sizes or different learning rates, the performance remains consistently high. This indicates that our approach is not only accurate, but also robust and practical for real-world deployment. Finally, we present several additional analyses to demonstrate robustness and practicality. First, we look at per-batch inference time. Our method has slightly higher latency than the lightest TTA methods, but it remains comparable to other strong open-set TTA approaches while achieving the best OSCR. This shows that our performance gains do not come with a large computational cost. Second, we test different ratios of known and unknown samples. In real-world deployment, the amount of unknown data can vary significantly. We observe that traditional TTA methods degrade rapidly when the proportion of unknown samples increases. In contrast, our method remains stable across a wide range of ratios, which demonstrates its robustness. Third, we vary the number of unknown classes. As the number of unknown classes increases, many methods show unstable or decreasing performance. Our method, however, maintains consistently high performance, indicating that it scales well as the open-set difficulty increases. Finally, we evaluate the model under gradually changing streams, which better reflect real deployment scenarios. Again, our method remains stable, showing strong adaptability to continuously evolving test environments. To summarize, existing open-set TTA methods discard all unknown samples. We show that some unknown samples are actually useful. Our method selectively learns from these samples using dynamic thresholding, OT-based refinement, and prototype weighting. This leads to consistent improvements across multiple benchmarks. Thank you for your attention.